Hello, everyone. This is Spencer Snolling from Hatch, and I'm glad that you could join us today for this month's GPSX webinar, where today we're going to be talking about simulating high-strength co-digestion treatment. And by that, I mean we're going to look at anaerobic treatment, and we're going to look at characterizing high-strength wastewater as if it was coming from a food processing waste or FOG, FOG, and we'll talk about how to use that in your model and get some really interesting results and useful information from putting that in your digester and seeing what happens. Okay, so as per usual, I'm going to be doing some slides and my desktop demonstration. If you have any questions along the way, please feel free to type them into the GoToWebinar questions box, which you can pop out of your panel there. And we'll just let those accumulate as the conversation is going on, and then I'll stick around at the end of the webinar to answer as many of those as I can. All right, so my plan for today is to, first of all, just introduce and make clear exactly what I'm talking about when I'm referring to co-digestion process. We're going to talk about how you model it in GPSX, and there's sort of three elements to that. I have some information on characterizing high-strength wastewaters. I'll talk a little bit about the Mantis 2 model mechanisms that are relevant to the digestion process. And also, I'm going to talk about setting up dynamic fog deliveries. And by that, I mean using the truck icon to represent an intermittent batch that is brought delivery of some waste and added to your digester. And as usual, I have a couple desktop demonstrations that I'll be putting together. And then lastly, of course, I'll answer any questions that you might have. Okay, so co-digestion is basically the process of adding some very high concentration organic waste materials to your feed at your wastewater treatment plant. And typically that is done by adding it to the anaerobic digester. That allows people to be able to accept waste from nearby facilities and to be able to increase their gas production, but there's also some downsides, which I'll go through here in a moment. So typically those high strength organic waste materials that are coming in consist of FOG, that's the sort of conventional short form that we use, fats, oils, and grease, and also food scraps and other food processing waste streams. I've had a couple of projects in my career where we had to include that, such as one in particular that I found really interesting, where we were including a waste stream that was coming from a winery. So typically these things are mixed along with the primary and secondary sludge and then sent into that digester. And sometimes that's done in various different ways. There's a number of facilities that I've worked at that had dedicated food waste receiving stations that made it nice and easy for the operators to come in and accept that waste in an efficient way. So the benefits of doing that are obviously increased biogas production. So you're putting a lot of easily digestible waste into your digester. So hopefully you get a lot of growth of methanogens and you get a lot more methane off of your system. And that will therefore allow you to, with that increased methane, maybe burn that and get some more energy recovery out of that, or use that as an offset if you're keeping track of your carbon footprint. Also, it allows you for some revenue potential for your facility. Typically these are situations where there will be a fee associated with bringing the waste to the treatment plant. So that would give you a bit of income to help pay for your operations. And if you're looking at it from sort of a very municipal wide point of view, it also is going to keep a lot of your organics out of your collection systems and out of your landfills. So if you are able to set up a FOG collection system for your restaurants and other food processing facilities, and they are having that kept on site and then trucked straight to the landfill site, straight to your wastewater treatment plant, that's very useful. You don't end up with that problem where you have a lot of fat in your sewer system causing blockages and so on. And it keeps all that material out of your landfill and keeps a little bit more life to your landfill system. So, and by putting it in the digester directly, you're removing that organic load from the aeration system too. You're not paying a lot of air to be able to, oxidize all of that carbon. And so that way, that's a little bit of an energy savings on top of being able to produce some energy from that methane too. And also, it's a nice alternative for those local food waste producers. I saw a really good talk actually at a workshop at WEFTech about 5 or 6 years ago that had some first-person experience from somebody who was working in Texas, where it's a bit of a remote place, and so it was really useful for the local economy, for the food waste processing places and the restaurants and so on, to have a place that they could take their food waste and get rid of it at a very economical price, because that was being operated by the municipality itself. However, there are some challenges, of course. You basically need some excess digester capacity in order to be able to accept that waste. If your digester is already being challenged and then you put in a lot more load, then that's not going to work out well for you. You'll end up with a process upset. So as I'm going to be showing here a little bit later by running some simulations, you can cause a decrease in pH, very significant decrease in pH. There could be a lot of foaming. There can be some struvite if you have a lot of nutrients in your incoming food waste as well. One of the background materials that I was reading in preparation for this webinar, actually where I got this photograph from, had a really excellent explanation of how one particular facility in California was really challenged by the fact that they were set up to receive all of this fog, but when it arrived, it had a lot of grit and stones and other things in it that made their life really difficult, and it really wore out their equipment very quickly. So that is a challenge there. If you were receiving, pure grease with nothing in it, then probably you're all set to go. But otherwise, you have to do a little bit of pre-treatment on that fog before you can put it in your digester. And also there's the variability, both in the concentrations that you might have and the pH, and also, in the time when are you going to have very reliably the same amount of fog coming to your plant every day, so you can sort of plan for that? Or is it, you might get 5 trucks on one day and then no truck on the next day. That could be a challenge for you. And operationally, these are possibly complex things as well. You'll have certainly increased traffic, especially if you don't have a nicely designed receiving station, so you get a lot of trucks coming and going. The fog itself is, of course, very acidic. It has a low pH, so it can cause a lot of corrosion on the hardware that you might have around to be able to process and all that. And in general, many of the things that I have read and talked to people about is that, in general, it's very messy. It's really gross and lots of odors and so on. So you have to be very good about keeping the operation pretty tidy. And then, of course, if you're going to be investing as a municipality in the capital that it requires to build, these receiving stations and so on, you want to make sure that those things are still going to come to you in the future to make it worthwhile to do that. So that's really about that variability in what's going to happen down the road. Are we still going to continue to receive all that food waste? Okay, so basically, this allows a lot of sort of degrees of freedom and areas in which you can use a model to sort of investigate what is going on in your system. So there's a lot of benefits to being able to model these types of co-digestion scenarios. Basically, the one thing that models are really good is figuring out how much capacity you have for something. So in this case, you could figure out, working from your existing system, if I modeled that, tells how much extra room, how much extra of that food waste could we accept and not upset our digester. You could therefore, next step in that process would be then, okay, well, how much energy and or nutrient recovery does that give us? Well, how much potential do we have to capture all of that? And then at the same time, you could look at evaluating the risk for liquid line process impacts. So here in this particular diagram, for example, our gravity thickener overflow is coming back to the headworks, and so is after the digester from the centrate is coming back as well. So, operations and things going on down here will eventually affect the liquid line if you have that type of recycle at your plant. So you could use a model to determine whether that's going to be a problem for you or not. And lastly, economic analysis as well. So you are able to, in GPSX, plot and calculate the amount of energy that can be captured, the amount of nutrients that can be recaptured. how much of the tipping fees that you could potentially accept without upsetting your system. And without getting into a lot of detail there, I did actually do a webinar on that only a few months ago, called Using GPSX for Economic Analysis of Biosolids Management. So if you go to our YouTube channel and go to the webinars playlist, you'll be able to go back and find this. And I've gone into quite a lot of the other options for it there. Okay, so there's three important things that you need to know when you're setting up your model to be able to model the co-digestion process. First is you need to do a proper waste stream characterization. So you have to have some time setting up how to make sure you've defined what that new waste is that's coming in. You also have to understand how this new waste stream is going to affect the behavior of that anaerobic digester. So there are some digester model features and parameters that you can tune for calibration, and I'll go through an example of that shortly. And lastly, I'll show you how to set up a dynamic loading. So you can have trucks coming at certain times of the day with certain amounts of loads and so on. So there's many other aspects that you could potentially choose to do with your co-digestion simulations, but I'm going to just stick to talking about these three important ones today. Okay, the first one, characterizing high-strength wastewaters. So basically, there are two potential situations that you could be running into when you're setting up your model. So the first one is that you have a full plant model. And by that, I mean you have both the liquid train and the biosolids train together in the same layout. So the stuff that's going into your digester is not, in this case, something that you set directly yourself. It is, of course, calculated by all of the upstream modeling work that you've done there. So, what comes out of the thickener is what comes into the digester. So the characterization in this case is really about what's in your influent. So in this case, characterizing the correct amount of inert solids in your influent will have an effect on what's going into your digester. Now, the other option is you actually don't model the whole plant. You only model the solids train, and you're doing that separately. So in that case, what's going into your digester is directly set up by you, and you have to specify that for one or more influent characterizations that you've got going here. So I have an example of one of each of these two things that I'm going to show you a little bit later. So Influent Advisor is your friend. It is a tool that you want to use when you're trying to set this up. And the one thing that you would typically have an issue to deal with here when you're setting up a high-strength food waste or FOG is that it's going to be a long way away from regular, normal influent wastewater. So all of our default settings that we're going to have in the menu there probably don't apply. So what you're going to do is you're going to enter the known concentrations that you do have for your food waste, identify the problematic calculations. As you know, it specifies any issues right off the bat by showing them in red. And then we're going to have to adjust some parameters to resolve those outstanding issues. So now, as I mentioned, our defaults and a number of our setups here that we have in Influent Advisor are geared for regular municipal influent wastewater. So now we're talking about something that is way more concentrated than that. So some factors might be okay, but we're going to have to make some adjustments in order to get things in the right place. As you can see, if you just type in a COD number, if that's the only number I have, then you're going to immediately see that you've got some very large negative concentrations that you have to deal with by adjusting the stoichiometry of your influent. Okay, so I'm going to show you an example of doing that. So for characterizing a FOG, basically you're looking at starting with a COD number that you may take from a measurement or some default value that you've gotten from the literature or someplace. This is going to be a massive number, hundreds of thousands of milligrams per liter. So you're going to enter that in, and then you're going to try after that to if you have measurements for this, that's fantastic. A lot of the times we don't. But you're going to be looking at a very much larger value, sort of typical ratio of bringing up the ammonia and phosphorus and soluble phosphorus up to a number that is sort of in the same kind of ratio that you would have for your other waste. Now, what those COD to nutrient ratios are like is really dependent on the food waste itself. So for FOG, basically these kinds of numbers are something that will get you into the right neighborhood. So we're talking hundreds of thousands of milligrams per liter of COD, something in the neighborhood of many hundreds or some thousands of milligrams per liter of the nitrogen, and hundreds of milligrams per liter of phosphorus. Those are sort of the kind of numbers you'd typically be looking at. And the other thing that you're probably going to have to do too is make some adjustments to the organic fraction. So pushing that total amount of your 400,000 milligrams per liter of COD, pushing it into the right place. So basically, you're going to probably reduce some of these numbers here. Typically, fog doesn't have a lot of particulate inert material in it, so you might back that down a little bit. By reducing these numbers, what you're doing is you're pushing it into the slowly biodegradable substrate state variable. And in that case, you are basically defining it as being like biodegradable, available to be used and available to be digested, but it's going to be on the somewhat more slowly biodegradable section. It isn't too important whether it's readily or slowly biodegradable in a digester, because of course it has that long residence time anyway. But anyway, reducing these numbers, particularly the inert part, will push it more into the biodegradable section. And then these two values here are also very important. So the number here you would typically see is something like 0.05. That is referring to the amount of nitrogen and phosphorus that are 0.05 for nitrogen anyway, are the amount of nitrogen that is bound up in the inert material. And so that's based off of a total COD number. Now, in this case, we're not looking at, like, this number was determined from things that were not 100, hundreds of thousands of milligrams per liter. So these numbers are going to need to be very much smaller than you had previously, or otherwise you will end up with negative numbers. Same thing for phosphorus. And then lastly, of course, you have a pH value here in your influence. So this may be somewhat lower than you're used to. So just to summarize all of those things, all of that rambling that I just did, your COD, ammonia, and phosphorus are often going to have to be 100 times to 1,000 times the typical municipal influent wastewater concentration. So right off the bat, you're going to be entering in very large numbers compared to what you're used to. And the majority of that COD should really be pushed over to the slowly and readily biodegradable substrate. That's what fog is ultimately. And then those nutrient fractions, N fraction of inert material, needs to be lowered typically to avoid negative concentration. So you might find that you've got to set it to either 0 or 0.0001 or something like that. And then typically you're going to lower the pH down for fog because it's going to come in a sort of an acidic state already. Okay, so that was fog. Now I'm just going to briefly touch on food waste. I really can't show you any typical numbers because they vary widely depending on what the food industry is that you're accepting the waste from. So you won't probably be surprised to find out, yeah, it really varies. If I'm dealing with something from a meat processing facility, that's going to have very different kind of wastewater than if I'm getting it from, a pasta factory or something like that. So these are all things that are situations where you're going to have to do some sampling to understand that kind of food waste coming in and what is its relative biodegradability. I've noticed through my experience over the years that ratio between the COD and the amount of nutrients coming in, nitrogen and phosphorus, is truly all over the map. Like, I worked on a project that was actually a meat processing facility. It was an abattoir. This was several years ago, that had a very high ammonia to COD ratio, much higher than you would have in regular wastewater. And then I've also worked on other ones, like a rice processing facility where they had to add nutrients to the wastewater to allow it to be released into the sewer system so that it could go to the plant, because it was so low in nutrients, all COD, no nutrients at all practically. So you can have it all over the map. And so one other key thing to keep in mind too is that the inert COD fraction of that COD coming in is really important to your gas production. So, and it might quite vary a lot depending on what kind of food is being processed there. So if I took at the total amount of COD that's broken into the inert and biodegradable parts and all of these other parts that make up our model, that inert side doesn't really contribute anything to methane production. So, and the key thing is, and I'm borrowing a couple of slides here from a presentation made by my colleague Zhu at WEFTEC in 2021, if you want to look up this paper. is that it really varies across the different kinds of food waste. So in yellow here is the percentage of the inerts based by COD of all of these different types of food waste. So you can see that in many cases there's a huge number of inerts, you know, particularly here for these meats as well. It's showing compared to, say, you know, potato peels and grass and other things that have a very low amount of inert. So you look at this list and it is truly all over the map. And of course, that's such a key thing is the, you know, the loading to your digester. If it's got a lot of inerts in it, you're not going to get as much gas out of that. So the side story of that, or the conclusion to that, is that really got to do some sampling of that waste coming in to understand what that composition is. Excuse me. Okay, so that was basically about characterization. That's probably the most important of the three things that I'm talking about today. Now, I want to get on and talk about how our anaerobic model works so that you can understand what's going to be happening in the background when you're using it. So the Mantis 2 model has, of course, a large section of it that is the anaerobic digestion process. And just for the record, by the way, it's exactly the same in Mantis 3. Our GHG model uses exactly the same anaerobic digestion model as Mantis 2. So there's some slowly biodegradable substrate that comes in and undergoes hydrolysis to become fermentable COD. The decay of all of the biomass is going to produce other COD that can also be fermented eventually. Then there's a number of different types of fermenters that are in the system producing propionate, and then essentially producing acetate. That's sort of the main story of what we want to get to here, is being able to you know, go through that acetogenesis process and get to acetate. And then we have a couple of different kinds of methanogens that are going to produce methane and also CO2. But right now, getting down to this methane here, this is the thing that we're most interested in dealing with when we're talking about co-digestion. It's sort of one of the main benefits is to be able to capture that energy that's stored in the methane. So basically, we want to understand what's happening with these methanogens in the model. Now, I was going to put up a lot more detailed math here to put this together, but the equations got quite long and complicated to explain. So I kind of simplified it down just a little bit here. This is the methanogens growth equation in our model. So I want to explain what these terms are here so that you can kind of get a feeling for why it's behaving the way that it does. So this is the rate of growth. And it is, of course, a first order relationship. That means here that I'm multiplying this growth term here, maximum specific growth rate, times XACM, which is our methanogens, the amount of methanogens in the system. So that's a first order rate. And then we multiply by all of these inhibition and saturation terms as we go down the list. All right. So just very quickly to explain what those are, we have to have some acetate present. We have to have some fermented COD present in order for things to go forward. We have to have inhibition terms for oxygen and NOx. This is the part of the equation that makes sure that it only goes forward if it's anaerobic. So we need the absence of oxygen and the absence of nitrite and nitrate. Then we have a section here, which is multiplying by these saturation terms for ammonia and soluble phosphorus. And this is our requirement that there's at least some nutrients available for uptake as a nutrient. So that all that part of it there just basically makes this run forward if there's food, if it's anaerobic, and if we got nutrients. And then it's these last two that are the real important ones that I wanted to talk about today. These are inhibition terms for ammonia and for the acetic acid. So this one is the one that is relevant to the fog situation. So what this is saying here is that if our sort of non-ionized or undissociated acetate gets up to a high enough level, then it becomes inhibitory to the methanogens. And they're actually fairly sensitive to these two terms here. So if one of these, if that term on the bottom, this is the ammonia here, this is the acetate here, if one of these two terms on the bottom starts to get much higher than the half saturation, than the inhibition term, K, then these things start to, dial down the growth rate automatically. And that means less biomass being grown, and more importantly, less methane being produced. So this is the term that's going to be sort of activated when you overload your digester with fog. And so I just wanted to let you know, if everything's hunky-dory, everything's running great, this term is going to be basically close to 1. So you're multiplying the rate by 1. Everything's great, no inhibition. But if we get some high concentrations of acetate, then we start to get into trouble. And this thing starts to become less than 1, and then it's heading on its way to 0 if we get really, really bad. Okay, so those two terms that control the inhibition are actually found on the kinetic menu. So you can right-click on the digester, go to Input Parameters, go to the kinetic menu, and then scroll all the way down to the biomass. If you've done this before, you know that we have a section on this menu for each of the different biomass types. It's quite a long menu. So this one's towards the bottom. Go to the acetoclastic methanogen growth, and you'll find these two important terms here. So you can actually plot the acetate itself, the total amount of acetate, and then also the non-ionized form by going to the concentrations menu. So here's the total amount of acetate. And if you go to the pH menu and scroll down past the pH and alkalinity, you get down to these undissociated concentrations of acetate. This is the one that is going to activate that inhibition term. So not only is it a function of the amount of acetate present, but also the pH. Okay, so that's enough talking. Let's get on with doing some actual simulations here. All right, I need my instructions. Here we go. And so basically, just to explain, you remember back earlier I mentioned about how you could either model this as just the digester part by itself, just the biosolids part, or do the whole plant. I'm going to start with doing the simpler one first, which is basically dealing with just the biosolids part of the system. So here I've got a primary sludge and a waste-activated sludge coming into this gravity thickener, and then it's going into this digester. And this is where we're going to add the fog. So that's going to be coming in. I'm going to do just steady state in this particular example, and also have the ability to do some chemical dosage here to sort of battle the pH problems. But for the most part, I'm just going to let it go and see what it does. Anyway, all of that sludge comes out, it's dewatered, and then land applied. All right, so we're going to hop over there, and I'm going to run just a steady state solution. And we can see here this digester is doing fairly well. So we started it out. This has been set up as if this was the biosolids handling section of a sort of a 5 NGD plant, roughly in that neighborhood. So I'm starting out with no fog. So you can see the fog amount here is 0 meters cubed per day. And so we can see here that we've got a certain amount of gas production and everything's going well. So I'm going to roll this up a little bit. Here you can see the pH right here. That's 7.27. That's fine. And then we can see our VSS destructions 53. Here's 1440. That's the amount of our gas that we have coming in under this no fog addition scenario. Okay, so let's add a little bit and see what that does to our situation. So I'm going to move this up here around 10, and I'm going to run it again. Steady state solution one more time. So our pH came down. It was 7.2 before, now it's 7. And our gas rate like more than doubled. So this is a very rich, a very energy rich type of organic waste that is easily digestible. So we got a huge response from our gas there. Okay, let's keep moving it up there. And I'm going to run it again. And we can see now we're up to 5,600. Our pH still continues to go down. And so that's telling us that, you know, things are sort of moving in the direction that we would expect. So what I'd like to actually do is actually sort of what I was doing is a very manual form of doing a steady state sensitivity analysis. So let's actually do that. I'm just going to reset everything here. I'm going to switch this over to a analyze step. So now I'm going to run a steady state solution at a whole bunch of steps along from 0 fog up to 80 meters cubed per day of fog. And we'll see how that goes. All right, so I'm going to turn this on. I have a number of graphs set up over here, and I'm just going to let it do its thing. Okay, so just to sort of explain what we're looking at here, these 4 graphs, the x-axis down here is the amount of fog being added, at steady state. So this is in meters cubed per day. So let's take a look at the pH first. So we can see here, it starts up here around 7, where it was when we were playing with it earlier. And we can see that the more fog that we add, then, and of course, it's bringing in that, readily biodegradable substrate, which is going to be fermented, which is going to become acid, and therefore it's going to drive the pH down. We can see that happens up here around, where's this? This is at more, I guess, around 60 meters cubed per day. Roughly, it starts to fall off the table. So that has a huge impact, you can see there. And of course, the biogas production, adding more of the fog, it gives us a lot more gas, but then it hits that peak here just around the time when suddenly the acetate takes off here, because now the system's no longer able to absorb and actually make use of that. The acetate is inhibiting the methanogens, so the biogas production falls off, the pH falls off. Suddenly that sort of non-dissociated acetate is now becoming a real problem, and we can see that it spikes up here. So this tells us a good capacity analysis here. We can say, well, we could accept maybe 30 or 40. This is sort of a comfortable spot maybe where we could do, and we've gained quite a bit of biogas production from that. But we now know where the cliff is. We don't want to get too close to that. Okay, so let's go back here. And lastly, I wanted to talk about setting up dynamic loading. So again, this would be bringing in a short-term, high-concentration batch delivery of something to go in your digester. And in that case, we're using the truck influent object. That we call it the batch influent, but it's basically the one that looks like a truck. It has two options. One, you can type in an average amount of flow, and we just spread it out evenly through the day. And that's fine if you're doing steady state or what have you. But really what most people want to use it for is to schedule individual loads. So this is just like a regular Influent object in the sense that you'll have to open up the Influent Advisor menu and type in all the concentrations and do all that work that I mentioned in the first step. But now you can also schedule when you want all this stuff to be delivered. So this repeats every day, and I've got it set up here in this little example of having 3 truckloads of 5 cubic meters each. And then this is starting and ending for the dumping of the stuff into your digester. And this is like a 24-hour clock. So this is 6 a.m. to 7 a.m. It puts in that 5 meters. Here's another one that starts that's 2 hours long, same volume, but spread over twice as long. And then again, lastly, we have 5 meters again over an hour. So you can see that what we do is we basically take this full volume and we spread it over, evenly spread it over however long it is that you've got this scheduled to happen for. So I set this up to show 2 1-hour ones and then the same amount spread over 2 hours. And that's how you control your truck deliveries. Okay, so now what I want to do is I want to go back to GPSX again. And I want to show you an example of that, just so that you could see what that looks like. Now, this might not be a hugely realistic setup here, but I wanted to do something that had a lot of sensitivity to it and was interesting to look at. Probably when you model a real plant, you'll find that it's not nearly this catastrophic, but I wanted to put something together that kind of illustrated the sensitivity of the model really, really well. Okay, so I've got a regular activated sludge plant here, primaries. I got a nitrifying plug flow bioreactor, secondary clarifier. By the way, this is a much smaller plant than what I was showing you before, just so that you know it's half an MGD. That's our default plant size when you put these object sizes down on the drawing board. And then it's got a full biosolid side here, so all of that sludge is being taken to this gravity thickener, and then we're adding in the fog before it goes to the digester, centrifuged, and then hauled away. Right, okay. So what I want to do now is I want to run a 1-day dynamic simulation. So let's just get that started. And in this case, I'm just going to take a look at this effluent. I've got this set up so the effluent is fine. It's fully nitrifying. The clarifiers are big enough that, we've got around 10 milligrams per liter of solids. And everything's hunky-dory there. And I think our mixed liquor bioreact, well, it's a little on the mixed liquor is a little lower than normal. It's like 1700, so that's fine. And then we've got our digester performance here. So right now I'm running it without any fog deliveries at all. So this is 0 showing along the bottom of this graph. And here in red, this is the biogas production. And you can see here it actually does fluctuate during the day. And that is because there's a daily diurnal pattern of flow coming into this system. So therefore, the amount of solids kind of goes up and down a little bit during the day. So that means there's a little bit of a fluctuation, a little bit of a pattern to the amount of solids being sent to the biosolids handling side. Right. Okay. So now what I want to do is I want to run this as if it's been running, you know, just normally. We're not bringing in any fog, and we're going to let the digester and everything kind of come to a good position. And then I'm going to bring in some trucks, and we'll see what happens. So first of all, I'm going to run this for steady state without any truck deliveries at all. And so let me see here. So what I want to do then is I want to bring in one truck at the 6 a.m. spot. So what I tried to do was set this up. There's 3 different deliveries here, just kind of like I was showing on that slide earlier. A volume and a starting time and an ending time. And then this is truck number 2 and this is truck number 3. So for truck number 1, I'm going to add just 1 cubic meter at the beginning. And I'm going to continue this, and we can see what impact it has on the system. So we can see here, regular pH here of 7 point something. That's pretty good, just like it was before. And this was starting out in the same place it was before until that delivery hit. And then suddenly we had a huge amount of gas production, which of course makes sense. That's what we were expecting. And we can see there was a little dent in the pH here. We can't really see anything specifically significant on the amount of acetate kicking around. So we've got just the littlest hint of a pH issue happening there, a little bit of a reflection. So this is telling us that, you know, we can take that one-time delivery without too much of a problem. Okay, so now what I want to do is I want to do that again, except instead of having just a 1 here, I'm also going to have another delivery that's at 10 a.m. So one at 6 a.m. and one at 10 a.m., both for 1 hour, 1 cubic meter that's delivered. One of them's over an hour, the other one's over 2 hours. So let's try that. So a couple of little variability in our loading scenarios here. So our pH is okay, and I've got an issue with the scale on this graph here. Just let me change that there so we can see what's going on. There, okay. So, yeah, it auto-scaled on me here. So just let me, there we go. Okay, so now we can see we've got our early delivery, really quick one, and then our slower delivery a little bit later in the day, and then this is kind of running along. And we can see here, you know, clearly a hump, and we can see that the pH kind of went down a little bit. Not too bad. I'm going to just push this out and let it run for the whole rest of the week now. And it's going to repeat those same 2 deliveries every day. So, but I want to do something different. I want to start ramping this up. So I'm going to allow a 3rd delivery of 3 cubic meters in the afternoon slot. So that one's going to be starting at 3 p.m. Until 4 p.m. So you'll be able to see here, that was the first one, then the second one, and then there'll be a 3rd one that's quite a bit higher. And we can see now that there's definitely starting to be an effect on the pH. We're seeing the gas is really up and down quite a bit during the day. Here's our other big load that's coming. So there's a big spike happening. And then I'm just going to keep doing this as a kind of sort of dynamic capacity analysis. So now we're going to say the loads are 3 cubic meters each during the day. So we're in the middle of the night now, and it's going to start up at 6 a.m., another load here. And you can see it does recover a little bit when there's not loads coming in right now, but the next set of loads is going to knock it one more time. So here's the first one. You can see the gas is going up. You can see the pH takes a hit right away. And there's going to be another load here, and then another load again. So eventually what will happen is if we keep increasing these things, it will get to the point where it doesn't actually recover in between. So I'm going to push that all the way over to 10, just to make it like an extreme situation here. Oh, by the way, you can start to see that even when we did those 3 of them back to back here, we're starting to get some accumulation of acetate here. And so the next time this comes around, we're going to have 3 really big loads of 10 cubic meters each. And I think that should kind of push us over the cliff at that point. So, but there's a lot of really interesting things that you can do with scheduling, optimization of scheduling of these particular units. These by doing this, what you're doing is you're really doing that kind of stress testing of your digester and of your system altogether. And by spacing them out, or maybe bringing them in at a slower rate, or maybe different kinds of composition, not all like the most highly concentrated stuff all the time. That'll kind of help to, give you something interesting to work with on your model. And so you can sort of see what is it that this particular plant could achieve. So, all right. So what now we blasted it with these 3 loads here, and we can see that it's not doing well to kind of recover back to where it was before. And so you can see here this acetate starting to accumulate. It's now getting up into the tens of milligrams per liter. So it's kind of pushing its way towards, that value of that inhibition constant. So that means that it's now struggling to be able to continue growing methanogens at all. And so here's our next set of loads have come in now. So that's the 5th day. And so this is pushing this up. We kind of pushed it over the edge now. And you'll notice that even though there's fog coming in, we're no longer getting that response of the gas over here, because we've basically fully inhibited the methanogens at this point. And so anyway, if we were to let this run, this pH will eventually come all the way down to like less than 4. And we'll get the gas will kind of just trail off down to a very low value here, and this acetate will again continue to accumulate. So anyway, it's an interesting experiment to play with this dynamic aspect of doing this kind of thing. And basically, I've given you a demonstration here how to kill your digester in 5 days. Okay, so let's go back to the slides and wind things up. If you have any questions, please put them in the box now so that we can answer those afterwards. Okay. So just a few final thoughts. So basically, fog and food waste streams can be incorporated into your GPSX process analysis. I do it all the time, actually, in the various types of modeling that I do. We've actually recently included it in the simulator that we built for the WEF Operations Challenge competition. And for the first time the past year at WEF Tech, we included a food waste question, which was really interesting. Proper characterization is really key to getting accurate prediction. You need to get as much data as you can on what's actually in that waste that you're potentially bringing into your facility. The digester model is really sophisticated. It'll do a good job of reflecting the pH, acetate and ammonia inhibition terms under high loadings. As I was saying, it did have that ability to sort of buffer off and recover until you've overloaded it, and then it's never coming back at that point. And the truck batch influent object is your friend, and you can use it to effectively simulate short-term effects of bringing in those high loads.